Alright, so welcome to Physics 2211, Lab 3, Sophion Monga, and we'll get right into it, jump right into it. So the purpose of this lab, we got two parts. So the first part, we create a model of a star orbiting around a black hole, and the purpose of this model is to calculate the mass of the black hole once we are given the mass of the star. And the results of this part was that the mass of the black hole was measured to be 1.31 times 10 to the 34th. And for part two, we create another model, this time of a ship leaving the system of a planet and a black hole without crashing into either of them. The purpose of this model is to predict the motion of the planet and the spaceship using gravitational forces that are present in the system. And according to the code, our initial velocity was deduced or determined to be -4 times 10 to the 7th and 2 times 10 to the 6th for the x and y. And concepts used in this lab, we've got Newton's second law, which is F net is equal to change in momentum over change in time. The gravitational equation, which is the negative g gravitational constant times the mass of A and mass of B over the magnitude of the distance between the two masses squared times the unit vector of that distance. And then we also utilize the force decomposition. So for the parallel and perpendicular components of F net, and the equations for them for those are given right here. And we'll move on to our first glow script model, or the first part of this lab. So the system was a star, the surroundings was a black hole, and the initial conditions we're given is the mass of the star, gravitational constant, starting time, the x and y velocity of the star, you can see that in this loop right here, and the star orbits a black hole. And the things that I changed in the calculation loop of the of the code was the finding the initial and final momentum, the change in velocity and change in momentum, the dp dt, which is delta p over delta t, fnet set equal to that, and then we calculate the parallel component of fnet and the perpendicular component of fnet right here. And then in this highlighted block right here, we actually calculated the mass of the black hole by utilizing the gravitation formula, or manipulating it to find the mass. And then right here we also changed the code so that we can display the arrows while the code was running, and then a print statement to print out the mass of the black hole. So right here for our results, you can see the arrows right there, and the results we got are the fnet, parallel and perpendicular components of the fnet, and the average mass of the black hole. I say average because the source of error for this part of the lab was that the mass of the black hole changes slightly with every iteration, most likely due to small calculation or approximation errors made in the code, and so I added them all up and divided them by the number of iterations, and we have the average mass right there. For our second glow script model, the system is the ship, surroundings are the planet and black hole, and the initial conditions are the mass of the star, mass of the black hole, mass of the ship, the starting time, and the initial speed of the ship, which we actually have to deduce. Things changed in the glow script code on the right hand side right here. You can see in the first block we actually calculate the fnet on the planet by finding the force of gravity from the black hole on the planet and the force of gravity from the ship on the planet, and we add them up to get fnet on the planet. And similarly, we do the same thing, but this time for fnet on the ship. So we do the force of gravity from the black hole and the force of gravity from the planet, and then we add them both up. And then we also utilize velocity and position update formulas to update the velocity and position of the planet and then the ship right here. And the rest of it we left unchanged. And the results for this code you can see right here. The magenta line is the ship, so it starts on the planet and it starts leaving the system, getting close to the black hole as well. And you can see the initial velocity that I used to, so excuse me, the initial velocity that I used so that the ship could leave the system is -4 e to the 7 and 2 e to the 7. And some sources of error for this are human error of inputting the initial velocities, because we did deduces by trial and error. And the errors in calculating the mass of the black hole from part 1 can also lead to errors in this part of the lab as well, since we use the same mass of the black hole. And moving on to our extra questions for the what does it mean? The net force and rate of change in momentum are technically equivalent through Newton's second law. However, calculating both separately requires different components, like the momentum is mass and velocity. And for this experiment, we calculated dp over dt, and we deduced fnet from that. We set it equal and then found its components separately. And for the what if, after tinkering with possible initial velocities, I was able to find one that put the spaceship in an orbit around the black hole. And you can see the magenta line, the spaceship orbiting the black hole right there in the center. And the cyan one is the planet. And I ran it for 600 minutes, made sure that nothing collided. and the initial velocity is -1 e to the sixth and 1.1 e to the seventh. And that was it for this lab. So have a great rest of the day.